when discussing surfaces, we have generally thought of functions z of x and y. So the idea here is that if I have a surface in 3 dimensions, then you think about each point z as being a function of 2 points, say A and B, that live in the xy plane. So I can drop a vertical line down to the xy plane, and then that point in the xy plane is where x equals A and y equals B. And so if I travel along points where x equals A, then I can travel along all points on the surface where x equals A. Or if I travel along x equals or y equals B, then I can travel along all points on the surface where y equals B. So the idea here is that these surfaces are always points z that are functions of our points x and y. But that is not the only way that we can specify a surface. The surface does not have to depend on, say, the x and y points. The x and y points could also depend on some other parameters, and that is what I'm going to show you when talking about parametric surfaces. So recall that we had this idea of a parametric curve. That was a function that input one parameter, a real number, and then output a vector, say in 3-dimensional space. So a parametric surface is going to input 2 parameters, 2 real numbers. So the inputs are going to live in R2, and then output a 3-dimensional point. So a parametric surface S is going to be the image of a transformation R that is defined on a region R in the UV plane and has values in X, Y, Z space. The image of R under each point U and V in my region R is the point in XYZ space with a position vector R of UV being X of UV, Y of UV, and Z of UV. So we want to draw some pictures to help us break down that definition. So the first thing that I'm going to do is I'm going to draw a region R in the UV plane in 2-dimensional space. So here I'm going to imagine that I have some region R in 2-dimensional space in the UV plane. Okay, and then every point in that region R is going to map to a point in 3-dimensional space, X, Y, and Z. So for example, if I have a point, we'll call that point AB. That point will map to a point in 3-dimensional space using that function R. So I can pick a point, say here, that it maps to in 3-dimensional space. So you can imagine that every point in my region R is going to map to a point in 3-dimensional space. And so I'm going to again draw a surface in 3-dimensional space that corresponds to the points UV in the UV plane. So that's going to be my three-dimensional surface. I'm going to give one more attempt at it here. So this will be my three-dimensional surface. And I'm going to be able to specify that surface using points in the UV plane. So for example, if I let U equal A, then you can imagine that I could travel along points in R where U equals A, and then that will define a curve on my three-dimensional surface. You can also imagine that I can travel along the point V equals B, in the UV plane. And again, that would correspond to a curve on my surface in the three-dimensional space. So this point here is R of AB. That is given by three functions: x, which is a function of u and v, y, which is a function of u and v, and z, which is a function of u and v. So the z coordinate you can see on the surface. I could drop a little vertical line down to the xy plane, okay, and then this point here in the xy plane would be the point x of AB, y of AB. And then the height of that point is given by z of AB. So this is a parametric surface, and you can think about it as being a group of parametric curves that are all kind of being linked together. Okay, so you can think about the surface as being defined by a collection of parametric curves. I've drawn two of them for you. I've drawn a parametric curve where u is equal to a. So for example, if I let u equal a, then what I have here is r of a v, and v is my variable, and so what I have is a parametric curve, the red parametric curve as I change v. Okay, or I can think about v being a constant b, and then again I'm going to substitute b, a constant, in for v, and now I have a parametric curve that depends on u, and so I can imagine going across the green curve u, r of u. So you can think about the surface as being kind of a collection of parametric curves that we put together to form and join and make a surface. Now, we have some definitions that go along with our parametric surface. The parametric surface S is called smooth, provided that the component functions of R have continuous partial derivatives with respect to u and v, and moreover, the vectors r sub u, or dr du, and r sub v, dr dv, are non-zero and non-parallel at each interior point of R. So if I can take partial derivatives of R with respect to u and v and those are continuous, then we're going to call our parametric surface smooth. And we're generally going to only deal with smooth parametric surfaces. Okay, but these derivatives of r with respect to u and v, they actually they give us two direction vectors. And those two direction vectors are going to be tangent to the surface. So I'm going to draw these two direction vectors for you in the space below. Okay, so here, let's see, I'm going to have a tangent vector, and you can think about this as being just the tangent vector for the red curve r of a v. And so I have a tangent vector to the surface here. We'll call that tangent vector r sub u. And then I'll have another tangent vector. Let's pretend that it goes this way. We'll call that tangent vector r sub v. So that would assume that going this direction along that curve will take you this direction along that curve. And then if we go this direction along where u equals a, that'll take us this direction along that curve. Okay, so we have two tangent vectors. Okay, we're going to call them RU and RV. And so those are the tangent vectors to the surface. I'm going to just change the shape of RV just a little bit so I can see that it's tangent. And then there will be a cross product of RU and RV that is going to be normal to the surface. So we can define one more vector. That vector is the cross product of RU and RV. That will be normal to the surface. So I'm going to draw something that's perpendicular, okay, to both RU and RV. And that will be a normal vector to the surface. And these tangent vectors and these normal vectors, they're going to be helpful for us in later computations with these parametric surfaces.